So I'm guessing you guys had fun with the homework. The good news is that there's another one out. There's homework 4 out available, and it got posted on Wednesday morning, about Tuesday midnight, and the homework 4 is about support vector machines. It's basically this, the previous lecture, this one, the next one, and maybe the one after that. And the good thing is that at the end of this, in this homework, you'll be writing code again. You'll be implementing an SVM solver, and we'll be going through the algorithm today. And the interesting part of this you'll see today is, remember your perceptron code from homework 2? It turns out if you take that code and maybe change about 8 characters from it, you get an SVM solver. So if you threw away that code, too bad. Any questions about homework and such things? Yes?
This might be an after class question, but one of my questions was, what's the difference between SVM and a multivariate perceptron?
Well, SVM is a linear classifier to start off. Just like a perceptron or a Winnow or any of those things. A multi-layer neural network is a non-linear classifier.
Okay.
So the expressibility is different. They represent different sets of functions. The other thing is the support vector machine is simply a learning algorithm for learning linear classifiers. The good news is that there are so many of them. If you don't like this, there's another one. But they're all linear classifiers. They represent the same set of functions. It's just different algorithms that get you a hyperplane. Other questions? So just to remind you of the announcement, homework 4 is available, and maybe you can even get started with the experiment part today, this evening, and maybe even some of the other sections on today. Certainly not the kernel part, which hopefully we'll finish by the end of the next lecture, but you should be able to do at least half of the homework this weekend. So we are in the middle of the support vector machines lecture, and just to remind you, the game we are playing is we want to learn a linear classifier, and we want to learn the classifier by maximizing this thing called the margin. And in the last lecture we saw why maximizing the margin is a good idea, and we also saw that maximizing the margin is mathematically it can be reduced to minimizing the norm of the weight vector, W transpose W. So minimizing W transpose W will maximize the margin. And that's just a convenient observation, because now we can write our the learning problem as an optimization problem. So in the last class, towards the end, we were looking at this thing called the hard SVM, where we say find a W, W is your weight vector, find a W, can be some n-dimensional object, such that it minimizes, find the W that minimizes W transpose W. Question: if I just stop there, I say I don't have any constraints, find a W that minimizes W transpose W, what's the answer? Let's take one dimensional. Find X such that X square is as low as possible. Find X comma Y such that X square plus Y square is as low as possible. W is just a big list of such numbers. W transpose W is simply W1 square plus W2 square plus and so on. So what is the minimum of W transpose W? In the unconstrained setting, 0. If you don't have any information, if you don't have any training set, what you're saying is push the weights as close as possible to the origin. But of course we have constraints, and the constraints are all of this form in the hard SVM. Remember that W transpose X is the same thing that we use for prediction. We take W transpose X and look at the sign of this thing. And if the sign is positive and Y is negative, then we have made a mistake. If the sign of W transpose X is negative and Y is positive, then we've made a mistake. So Y times W transpose X should be positive, should be greater than 0. And in fact, in your perceptron implementation, when you implemented margin perceptron, you did exactly that. You demanded that, in fact, you checked for error by checking whether y w transpose x is less than 0. And in margin perceptron, you allowed a margin. Y w transpose x is less than some positive fixed constant. That's what we're doing here. We're saying, find a w that minimizes the norm, and every example should be classified correctly. But not just correctly. In fact, y w transpose x is not just greater than 0, but greater than 1. There should be this gap, this margin of error that we are allowing, so that in the future, when examples come in, even if they are wrong, they might lie in this margin and we might be okay. And this is what gives us the generalization guarantee. In the last lecture, we saw how we can come to this intuition using the VC dimension and this theorem from Wagner. This was the hard SVM. And it's an optimization problem. And we saw that there was still an issue, because this is a constrained optimization problem, and if we demand that every training point should be correctly classified by some w, and it so happens the data is not linearly separable, there is no w that can correctly classify this. So this optimization becomes infeasible, and you're, depending on how you implement this, either you will get some reasonable answer or your program will throw an exception. So the data is not separable implies this solution is useless. And the answer we saw was, what if I identify these bad examples that are actually causing my data to be non-separable, like the minus here, throw it out of the data set. What if I identify other examples which are really there, which are okay, but they are forcing the margin to be very small, throw them out as well. And now with the new data set, I try to find the linear classifier, and I'll ignore these points and then maximize the margin. This objective is called the soft SVM. And the way we did that is say that by introducing this additional variable for every example called the slack variable. We call that psi I. Just realize that psi, in fact, those of you who were in the data seminar yesterday, we had a discussion about SVMs. Psi looks like the Greek letter epsilon. It's not, it's xi. And when I write it, I tend to write it as just a squiggle. But anyway, we introduce psi I for every example, and psi I is called the slack. The slack simply says how much should this example violate the margin constraint or not. So we want, but if so, by how much? So we want all the slacks to be positive, and instead of demanding that y w transpose x should be greater than 1, we are allowing y w transpose x should be greater than something less than that, 1 minus the slack. If all the slacks are 0, we come back to the hard SVM. So what we want to do is allow some slack variables to be non-zero, to be more than 0, so that they break into the margin. And this can be mathematically framed in this optimization problem that at first glance may look hideous, but actually is there's a pretty reasonable interpretation. So let's just to point out, the only big difference here is we've changed y w transpose x doesn't have to be greater than 1, but should be greater than 1 minus the slack for that example. And we've seen all this. This was one of the last things we saw in the last lecture. So just to interpret this, there's a w transpose w, same thing as before. What we are saying is minimize w transpose w is equal to saying maximize the margin. And in addition, we don't want all the slacks to be positive, because what will happen is otherwise, if you do not minimize the total slack, then basically we are allowing the learning algorithm to throw out the entire data set by saying all of these guys are causing me trouble, let me just throw it out, set w to 0 because we don't have any training data, and we are done. So we don't want that, so we want to in addition to minimizing the margin, we are minimizing the total slack. Subject to the same constraint, subject to the constraint that says each example, like the xi, yi, in the training set should be correctly classified up to the slack. Should have a functional margin, that's the name for y w transpose x. Every example should have a functional margin of 1 minus the slack, and the slacks are all positive. This is a well-formed optimization problem. And the nice thing about this problem is that it also has this parameter c. Sometimes you will see the c shows up on the w, or here they are the same, they are equivalent. And the way to interpret this is the first term here is pushing for the generalization, it's maximizing the margin. The second term says how well should you fit the training set, how well should the training set be classified. Because if all slacks are 0, the minimum slack, so if the first term was not there, suppose, then the minimum slack sum should be 0 because all the slacks are positive. And so all the slacks are positive, and if this term did not exist, minimizing the sum of all the slacks, the right answer is set them all to 0. That's the lowest value you can get. Setting them to 0 means this goes away, and we're back to saying that every point should be correctly classified. So setting all the slacks to minimizing just the slack alone forces us to correctly classify the data. Minimizing the norm of the weight alone pushes for generalization, and this parameter c here is like this knob that controls, do I want overfitting or overgeneralization? Both of them are actually, it turns out, not all that good. Instead of overgeneralization, the correct term to use is underfitting. Do you want overfitting or underfitting? And C is this knob that lets you say, I value the overfitting more, so let me control for that, or I value underfitting more. And one way or another, based on what you care about, you can pick an answer. You can pick a value of C. Typically, the way to pick C, and that's what you'll be implementing in your homework, is to do cross-validation. Just try out a few different C's, use cross-validation. You guys are experts on cross-validation, so I'm not going to talk about that. Questions about this? And this is roughly where we stopped in the last lecture. Yes? Why is SVM called SVM? Hold on to that thought. And I'm guessing you know the answer, so I'm not going to... someone else should ask me this question at some point in the near future. And I totally did not plant that question. So there's a reason why these are called support vector machines. And we'll see that maybe right after we see how to solve the optimization problem, because after solving the optimization, we'll come back to this objective and stare at it. Remote question.
Is slack some constant value? How do you decide what that value should be?
So the slack variables are not constants. The slack variables, if you notice, I was a little sneaky when I changed the optimization from here to here. I just marked this difference. But actually, I changed this as well. In the hard SVM, you minimize only over the W's. In the soft SVM, you try to find the best assignment for W and all the slacks together. So you're changing your optimization problem, you're making it a much larger problem, and you're trying to find a joint assignment to W and all the slack variables such that this objective is minimized and all these constraints are satisfied. Other questions?
So the answer to that is that we'll start with some number, whatever we choose, and then the optimization algorithm will take us to the right number.
Yes. And in fact, this objective has some fantastic properties. In particular, it's convex, so it doesn't matter where you start. You will end up at the bottom of this thing, and we'll get to that maybe in about 30 minutes. Yes, so roughly that's how the optimization proceeds. You start with the first guess and then keep iterating. But I'm going to make your life a little simpler when it comes to solving this optimization. But before that, this objective has all these terms. In particular, it's a constrained optimization problem. It's an optimization problem that you're optimizing an objective subject to constraints, and this kind of a problem is slightly painful to solve. Not very, but you have to keep track of a lot of things. In particular, you have to keep track of all the weights and the slacks. And actually, we can simplify this and write down an equivalent optimization problem by getting rid of the slacks together and maintaining the semantics of this object, this optimization. So we'll write a new optimization problem whose optimum W will also be the optimum W of this one. And if that shows up, we should be happy, right? Because all we care about is finding a weight vector. To do that, we can use some algebra to eliminate all the slack variables. Notice that from these two equations, in particular, let's take a look at this one. This simply says the slack variable should be greater than 1 minus y w transpose x. I've done nothing, I've just moved that around. So now we have two greater than constraints with the slack. The slack should be greater than 0 and it should be greater than 1 minus y w transpose x. Right? This means combining these two together, we get the slack should be greater than the max of those two things. Right? I've done no magic here. So the slack should be greater than 0 and 1 minus y w transpose x. But once I have this form, I can just replace the slack here, this into the objective here. So let me get rid of some lines. So I can replace xi from this inequality into the top and get rid of all the constraints and end up with a different optimization problem. So these two together tell me that so the slack should be greater than the max of these things, and I just replace the slack in the objective with this max term, and you get an optimization problem that is unconstrained. There are no constraints. So these two problems are exactly the same optimization problem, except the second one does not have any of these slack variables. Does the algebra make sense before talking about how to interpret this and why this is actually a much more interesting representation of the same problem?
So basically that summation is just over the examples that are correctly classified.
That summation is over all examples.
With there being max of 0 and...
Actually, not correctly, incorrectly classified.
Incorrect.
Incorrectly. In fact, that's an excellent observation. We'll be spending at least, more time on exactly that observation. But yes. So it turns out this form of the objective is much more interpretable because I can write this. I've just copied it out there. So you have minimize W, or saying find the minimum W for this function. Which function? The function is half W transpose W plus C sum over this max term. And the way to interpret this is the first term, as always, maximizes the margin. W transpose W says I like big margins. The second term should be interpreted as a penalty for misclassification. How much should this W, so effectively this, everything inside this circle here is some function of W. I'll call it F. And what I'm saying is, learning is simply search for weights, right? Learning is a search over this infinite space of the vectors to find the one that has the minimum value of this function. A stupid learning algorithm could be try a weight. Doesn't work. Try a weight, remember the value. Try another weight, remember the value. Exhaust the set of infinity, and then you will have your answer. Of course, we'll look at more intelligent algorithms for this, but way to interpret this function of the objective is the second term is simply penalizing misclassification, penalizing weights that misclassify more training examples. Now, to expand on this, let's look at 3 different training examples. So, and I'll draw a picture here with all these 3 examples. So, let's say you have a plus, minus, and let's say you have plus here. Clearly, this is linearly separable, first of all. You should see that this is linearly separable. I can draw a line this way, right? But let's say that during training at some point, our learning algorithm comes up with a different line which looks like this. In fact, let's have another minus also. Our learning algorithm comes up with another, is entertaining the possibility that this line is the right separator. And consider first, and with saying that everything on this side is positive. Consider the point here, the plus. This example is correctly classified, and let's say the margin, in fact, let's put up another plus here. Let's say this is the margin. Okay? This distance here. So, the big plus outside the margin is correctly classified, and it's outside the margin. In other words, y w transpose x for that example will be more than 1. Which means this max in the box up there, 1 minus y w transpose x will be less than 0. Y w transpose x is more than 1. And so the max is 0. So what that means is this w, this line here, I'm going to call this w. The w does not pay any penalty for this red plus. Okay, let's consider another example. Consider this plus. This one is misclassified. It's on the other side of the hyperplane. So y w transpose x is less than 0. What? Right? If it's less than 0, it's clearly less than 1. Which means that's the penalty you're paying. 1 minus y w transpose x is greater than 0. So the penalty that this weight vector pays for misclassifying this example is 1 minus y w transpose x, which is a positive number. Now consider a third example, this minus here. That minus is, the classification for that minus, is that right or wrong?
Correct.
It's correct. Y w transpose x is positive or negative? Positive. What about it? Whether is it more than 1 or less than 1? It's less than 1. So it's correctly classified, and yet it's inside the margin. So even though it's correctly classified, this particular weight vector will have to pay a penalty of basically this distance. How much is it missing the margin by? 1 minus y w transpose x. Because the max of 0 and 1 minus y w transpose x will be positive, and it will be 1 minus y w transpose x. So there are 3 cases. If the example is correctly classified and it's outside the margin, no penalty. If it's incorrectly classified, a big linear penalty. Linear in basically in y w transpose x. And if it's correctly classified and yet inside the margin, you still pay a little bit of penalty because you want to keep pushing the margin out. You would rather prefer a weight vector that puts points outside the margin. Question?
I'm having a little bit of confusion understanding how that first expression is maximizing the margin.
The first expression is maximized. Aha. In fact, that's roughly what we saw in the previous lecture. So remember that the margin is this quantity, right? And actually no, it's the max of this value, max over all the training examples. Find the, did I say max? I meant min. Find the point that's closest and the distance to the closest point. And what you will do is, instead of doing that, you will try to find, you will say that you set the closest point to be at a distance 1. That's what this constraint did. And then you minimize you find a W that maximizes this whole quantity, this whole thing. And that's equivalent to saying minimize the norm of W. Minimizing the norm of W is equivalent to saying minimize W transpose W. Yes?
Maybe I'm just confused, but I feel like a few slides ago we were trying to minimize W and slack. Right?
Yes.
So we were trying to minimize the whole thing. So is the minimization on the left for the whole thing, not just for the
This part here? Oh, I see. So this goes this way.
Yeah, that.
Yes,
right?
it's for the whole thing.
Okay.
Because the W is also part of the penalty now.
Yeah.
So the way to interpret this is the first part pushes for lower VC dimension actually, going back to the beginning of the previous lecture, or generalization. The second part wants your weight vector to correctly classify the training set. So, and you want to find a W that balances these two things. I want it to be correct and yet be good in the future, on future examples. Other questions? So, this function inside the box up here, inside the blue box, is actually a named function. It's called the Hinge Loss. And this is the first time we are seeing this term loss. And loss is just another way of thinking of, here's how much you penalize a weight vector, or in general, here's how much you penalize a model for making a mistake. So there's the classifier is completely defined by W. Say this W gets an example, X and Y. What's the penalty faced by this weight vector on this example? And the Hinge loss is simply defined as max of 1 minus YW transpose X. And the interpretation of the Hinge loss is these three cases. There's also a pictorial interpretation. And here I've plotted YW transpose X on the horizontal axis and the actual loss incurred by the objective on the vertical axis. And the red curve is called the 0-1 loss, or the misclassification loss. And the black line is called the Hinge loss. These are just different loss functions. These are just different ways of penalizing classifiers. The 0-1 loss says if Y and W transpose X have the same sign, that is YW transpose X is positive, that is on this side of the, to my left. The classifier, that particular weight vector makes no mistake, so the penalty is 0. To my right, the Y and W transpose X have different signs, so the product is negative, then the penalty is 1. So this is called the 0-1 loss. It's just saying, this is how much the classifier should pay if it makes a mistake on an example. Every mistake costs 1 point. So that's the 0-1 loss, and this is the ideal loss that we want to minimize, right? We want to minimize the number of errors. Unfortunately, there's a bit of a hitch here because minimizing the 0-1 loss is NP hard, which is why you replace it. Actually, if you want to think of it from the convexity point of view, the 0-1 loss is not convex, which is why you replace it with surrogate loss functions. And one of those surrogates is this thing called the Hinge loss. The Hinge loss is this black line, and it has these three regimes. When YW transpose X has the same sign, is positive, that is Y and the sign of W transpose X are the same, in other words the classifier is correct, and W transpose X is far away from the margin. In particular, it's greater than 1. Then that particular weight vector pays no penalty. The second regime is in this space here. If Y has the same sign as W transpose X, and that point is very close to the margin, so W transpose X is very close to Y W transpose X is less than 1, and greater than 0, then that particular weight vector still pays a penalty. How much? It's linear. If it's a mistake, you pay bigger penalties the larger your mistakes are. So if your hyperplane is, say this is your hyperplane, and you classify your point, you misclassify your point and you put it in a much farther away on the wrong side, then you pay a much larger penalty. And that's why it keeps going up all the way to infinity. Questions about the Hinge loss?
So if you get say one example comes in and you're really wrong on it, but really the example is really wrong, then you're going to pay a heavy price for a noisy example that's
You
an
might,
outlier.
and that's really where this the constant, that the hyperparameter C really makes a difference. If you set C to be very high, then in fact it's easier to interpret this in the equation. If you set C to be very high, then this penalty becomes huge. So your optimizer, it doesn't matter what algorithm you use, whatever optimizer you use, will try very hard to correctly classify that point, even though it's noisy. If you set C to be very small, then it would be less or more inclined to get rid of that point. To say that, yeah, this is noise, let me just pay the price because I'm getting some extra boost through this W transpose W, the first term. And that's why C controls between overfitting and underfitting. Underfitting simply says, I'm not going to try to explain every point in the training set. And hopefully, on one hand, if I underfit severely, then you'll explain no points in the training set, so there's no learning really. So that's why the C has to be chosen very carefully. The example that you suggested, in this case, you choose a small C. If you believe your data is noisy, you will choose a small C. If you believe that your data is perfect, you will choose a large C. Really, your belief doesn't matter. You should let cross-validation do that job for you. Other questions? So we've been switching back and forth between an algebraic version of the story and the geometric, and the reason for that is because this particular classifier can be analyzed in both points of view. There's a very cool geometric perspective here, and algebra lets you actually solve the optimization. Yes.
I don't know if this is interesting or not, but let's say we knew that our plane had to go through the origin, then it seems like, if I'm thinking right, then we want to just maximize the number of points that we correctly classify, because
But this plane goes through the origin, because there's
the weight vector, I don't know, maybe we should talk about it after class.
Okay. Yeah, there's actually a lot to think about this particular optimization, because there's some interesting geometry here, and that's one of the reasons why also a lot of people from the geometry community also jump in, and we can get interesting algorithms for SVMs just by analyzing the computational geometric perspective. But just a minor detour, probably this is the first time I want to introduce this principle called risk minimization. Risk minimization is simply, or it's also called loss minimization or empirical risk minimization, and it's the following idea. I want to train a classifier. In this case it's a linear classifier, in general, some classifier, think decision tree or anything. And I'm going to frame learning as the following. I'm going to give you right now a recipe for constructing learning algorithms. I'm going to let's define something called loss, something that mathematically defines what makes a classifier bad. An example of that was the Hinge loss. And then you write down a function that sums up loss over the training set, and you write learning as optimization problem that finds the classifier that has the lowest loss. or the lowest empirical loss. This is called empirical risk minimization, but that's not the complete story. We didn't have an empirical risk minimization, we had something called a regularized empirical risk minimization, or empirical, whatever, it doesn't matter. And the idea is, yeah, sure, I have this one term that says minimize the loss on the training set. But minimizing loss on the training set is not sufficient, because if you minimize the loss on the training set and force it to be zero, every point in the training set will be perfectly classified, but then you might overfit. So let's add another term to the objective. That term, in the SVM case, it's called the regularizer. That term pushes for generalization somehow. Mathematically, it somehow pushes for generalization, and one way we saw of doing that is to add the norm of the weight vector. Adding the norm of the weight vector to the objective gives us capacity control, or for example, in this case, lowers the VC dimension. So now the recipe for learning or creating learning algorithms is step number 1, define a loss function. The loss function takes, say in this case for linear classifiers, it takes a weight vector and a labeled example and says, will this weight, and somehow mathematically, numerically says, quantifies how much mistake does this weight vector make on this example. That's your loss function. Step number 2, write down a regularizer that penalizes complexity in some way or another. For example, if you have a linear classifier, the penalty for complexity is W transpose W, the norm of the weight vector. Then write an objective function that's the sum of your regularizer and the average, or the sum of the loss over the training set. So now you have a function. You have a function that can quantify how good or how bad is every possible classifier. And now you've reduced your problem to an optimization problem, and you can do one of two things. Hope that your optimization friends have already solved this problem, or you can somehow come up with an algorithm. This recipe is called empirical risk minimization, and it's a broad umbrella that can be used to describe most modern learning algorithms. Remember AdaBoost? It turns out AdaBoost fits under this framework as well. It just, you have to, it was not invented that way, but as an afterthought, people realized that the AdaBoost algorithm is actually minimizing a particular loss function called the exponential loss. SVM minimizes the regularized Hinge loss. Turns out the perceptron, good old perceptron, also minimizes a loss function called the perceptron loss. Turns out another algorithm that we'll see very soon called logistic regression minimizes another loss function. So many modern learning algorithms fit under this umbrella of empirical risk minimization, and if we can force our algorithm to be, or if we can write down an objective this way, we can actually define learning algorithms pretty easily. And these days, this has become probably the most dominant way of writing down learning algorithms. So in the last, say, maybe 10, 15 years, or maybe 5, 10 years, we've seen a lot of both popular press and academic chatter about deep learning. Deep learning talks about these giant, non-linear, really complex classifiers. And if I'm going to have to write down and define a new learning algorithm every time a new classifier is defined, there's no way we can make progress very easily. It turns out all of those things are fit into this umbrella of empirical risk minimization. Just write down what is the loss and reduce your problem into a mathematical optimization problem. So one word of advice, if you guys want to continue on this kind of thing, I would strongly recommend, in addition to beefing up on probability and statistics, also learn optimization, because if you understand optimization, now you can suddenly generate learning algorithms very quickly. So let's look at the SVM objective function from this perspective. There is the regularization term, the first term, W transpose W. What it says is, I like weight vectors that have larger margins. Maximize the margins. Implicitly what it does is it imposes a preference. It imposes a preference over weight vectors that are all the same with respect to the error, but only differ with respect to the margin. And we saw some theory that said that larger margins equals or implies better generalization. So the regularizer is a term, the first term is a regularizer that effectively does capacity control, makes the classifier less expressive and hence more general. The second term is the empirical loss. For the SVM case, the empirical loss is the Hinge loss. And it has this, all loss functions penalize mistakes made by weight vectors, and in this particular case the Hinge loss has this piecewise linear functional form, but you can replace it. There exist other loss functions as well. We'll see at least one or two more before the end of the semester. So there are these two terms, there's the regularizer and the empirical loss, and it turns out these two terms are at odds with each other. The empirical loss prefers functions that explain the training set, prefers classifiers that overfit. The regularizer makes classifiers less expressive and hence intuitively prefers classifiers that underfit. So we need this trade-off term, the hyperparameter C here, that trades off between these, which you as the designer of this optimization or as a user of this algorithm will decide either using some domain knowledge or more preferably actually by cross-validation. Questions about this? Yes?
So I figured out the point to ask my question I asked earlier. So what if we assume that the B, you know, the intercept, what if we knew ahead of time that that's 0? So then all we care about is like a direction.
Sure.
Then it seems like in that case, I mean, I don't know if this is interesting or not, but it seems like in that case then you could ignore that regularization term and you would only care about the empirical loss.
Why is that?
Because since you only care about the direction, you don't care about the intercept anymore. You could just consider.
But you can think of the B as being 0 even in this case. I'm always assuming that B is 0 because I've already added a constant feature.
Oh, right, well, yeah. So. I don't know, I can kind of visualize it in my head.
Okay, let's talk after class. Okay. Maybe you can either one of us can convince the other.
Yeah, okay.
Yes.
So you mentioned that any learning algorithm someone designs, it can be mapped in.
No. That's a very strong statement. What I said is many learning algorithms follow this.
So say for the case of perceptron, am I correct in saying that the loss function wouldn't have a regularization?
Yes, the perceptron is actually unregularized, and the perceptron loss looks almost identical to the Hinge loss, except it does not have that 1. We'll see exactly what that's, how to get there in maybe a few minutes. Yes.
So if you have a real value problem, regression type problem, so can we replace the Hinge loss with RLS?
Yes. In fact, that's a legitimate learning algorithm. It's called regularized least squares. For all loss functions, you can write down a regularized version of that optimization problem. And regularized least squares is probably one of the strongest regression methods out there, at least for it helps generalization.
In the case of linear classifiers, it seems like the regularization term is like less important because, like we said in perceptron, we didn't even have one.
Yeah.
But it seems like with really expressive learning algorithms, you would definitely want a regularization term to stop overfitting.
So you just made 2 points, and I'm going to address both of them. Your first point was that with linear classifiers, regularization is not important because perceptron didn't have it.
Less important, not
less important. It turns out that even for linear classifiers, regularization is very important, and that is actually the reason why average perceptron does better than plain perceptron. Vanilla perceptron is not regularized, and it hence does not have the pack guarantees. Average perceptron sort of comes with pack guarantees. So even for linear classifiers, regularization is very crucial. And in fact, in many application problems, what I have observed is changing the value of C can give you anywhere between a few points gain in accuracy to maybe 10, 15 points increase. If you choose a bad C, you can get really bad classifiers. If you choose a good C, you can get an excellent classifier. And that makes a big, big difference. So you should have cross-validation as part of your toolbox, and every time you are training a classifier, you should always cross-validate over these hyperparameters. Your second question though your second point is actually very valid. As your classifier, as the capacity of your classifier gets larger, so does the importance of the regularizer becomes small. If your classifier can express more concepts, then you want somehow to restrict this even more, restrict the space even more, and this gives a flexible way of restricting the expressivity through this optimization. Other questions?
So it seems like the regularization is kind of intertwined here, and that, like, just looking at norma W alone, I wouldn't say that describes a complexity or whatever of like a line, but somehow it's intertwined with like the empirical loss.
In this case it is.
Okay.
In general, you might just see a different function. So here, there are at least 2 or 3 different ways of introducing SVM. The way I introduced it, yes, it seems like it is intertwined. Another way of introducing SVM is to say that I want to minimize the regularizer plus the empirical loss. Here's the regularizer. It's a regularizer because it penalizes complexity. In other words, it basically says, if I think of level sets on the space, this pushes the weights to be closer to the origin, right? And that's a measure of complexity. How far is the weight vector from the origin? And the second term is the loss, so your regularizer plus loss can be minimized. The interesting thing is, even though in this sort of analysis, the way I introduced it through this margin, there are other regularizers even for linear classifiers. Because notice that W transpose W is basically the 2 norm squared. Right? I could replace it with a 1 norm. That has an interesting probabilistic interpretation. It pushes for sparsity. And so there are other regularizers even for the linear classifiers that are not directly tied to the other term. Other questions?
I guess one final question is, like, if we only, like, W is just basically determining the direction of a plane, like it's just like the normal vectors we're talking. And so if we scale W, that shouldn't change, or we kind of talked about this.
Yes.
If you scale W, that shouldn't change how you classify things, but
Here you are changing the scale of W.
yeah.
Because by actually in designing this formalism, we fixed the scale of W to be the functional margin of the closest point.
Right.
So,
Yeah, somehow that intertwined.
right.
Yeah.
So,
okay.
in this particular formulation, we demanded that we got rid of that degree of freedom to allow us to write an optimization problem. Yes?
And so the sparsity that you mentioned for reducing the dimensionality?
You can think of it that way, or you can, in fact, it's sparse in the same sense that, say, Winnow will learn classifiers that have, or actually not Winnow. It's sparse in the sense of it pushes for many of the weights to be 0. So if your true concept has many irrelevant, if your many of your features are irrelevant, adding an L1 regularization is a way of doing feature selection actually in this kind of integrated fashion. Other questions? L1 is the 1 norm. Yes. And we saw 1 norm long back when we were talking nearest neighbors about distances and stuff. Questions from this side of the audience? Okay, so
why is it called support vector machine?
why is it called support vector machines? Let's talk about that once we talk about how to solve the optimization problem. Notice that I have only written down an objective. Now, some of you might be experts in optimization, and at this point you probably know already how to solve it. But the rest of us, this seems like a big hurdle. I mean, just being able to write down this objective does not mean we've solved the problem. So, the next thing that we're going to see, and probably this will be the last thing for today, is how do you solve the optimization problem for this SVM. So, in other words, we have this function, half W transpose W plus sum of Hinge loss. And this is a function of W. We want to find a W that minimizes this expression. And if you're an optimization person, the first thing that you should try when you see minimize a function is this function convex? Turns out this function is convex. And to remind you what is convexity, let's take a brief detour. A function f is convex. Say a function, in this case, in this picture here, this function is just in the function of one variable. It's convex if the following property holds. For any u and v, and for any lambda between 0 and 1, f, if you measure the function value at a point between these two things, between u and v, anywhere between u and v, that's basically this point here or this point here, that value has to be less than the line joining f of u and f of v. So f of lambda u plus 1 minus lambda v should be less than or equal to lambda times f of u plus 1 minus lambda f of v. That's the formal mathematical definition of convexity. Intuitively, what this means is convex functions are functions that look like an upright cup, basically. Which means if you start anywhere and just, if you have a bowl or something and you put a drop of water on an edge, no matter where you start, if the cup has a certain shape, it will roll down to the bottom. And the reason for that is because that object is convex. Another intuitive way to understand convex functions is, for every function at any point, I can ask what's the tangent? The tangent line, or in high dimensions, it's the tangent plane. And convex functions are those functions where every tangent, meaning tangents at every point, lies completely below the plane, below the curve. Like this picture here. You draw the tangent at any point, and that is completely below the curve itself. So this is a convex function. Many functions are convex. Many functions that you've seen. So the linear function f of x is, say, x or minus x, ax plus b is convex. Squares or quadratic functions are convex, but not f of x is minus x squared, because f of x is minus x squared looks like an upside down cup, so it's not convex. For our purposes, max is a function, right? Max of ab is a function that takes two things and says picks one of them. Max is a convex function. In 2 dimensions, this is just some picture I think from Wikipedia. You have a quadratic paraboloid, that's a convex function. And there are many ways to check if a function is convex. The most naive way, and sometimes the only way, is to use the definition of convexity, see if it applies for all possible points at u and v in the previous slide. Or you can use some properties of convexity. Probably the most useful property is if a function is convex, actually if you take the function and you take its second derivative, if the second derivative is positive, the function is convex. Yes?
So I'm wondering, some functions, they're concave, like for example log of x.
Or minus x squared.
Yeah, but then you just flip it like multiply by -1 and it becomes convex.
Yes.
So could we perhaps replace convexity with monotonicity?
No. Monotonicity is just increasing. Convexity is a different property.
Oh, yeah, that's right. Okay.
Yes. Was that a remote question?
No.
Okay.
I was just drawing.
So we'll take the second derivative thing. What if you had a case where you had like 5x to like the fifth or something, so you still have an x term in your derivative, like.
You have to prove that it's positive everywhere, independent of x.
So the variable terms left over would have to be either like squared
or absolute value or something like that. Yeah. And that's for one-dimensional functions. And if you have functions that take more than one input, then the test is no longer positive because the second derivative of a multi-dimensional function is actually a matrix. And you have to prove that that matrix is positive, definite, or semi-definite. I'm not going to necessarily labor this point, partly because you guys saw positive, definite, maybe in your quiz 0, many centuries back. I encourage you to take a look at it again. It's a useful thing to know in general. Convex functions are useful, but sadly not all functions are convex. Some functions are concave. You just flip a convex function upside down, it becomes concave. And mathematically, that just changes the inequality from less than to greater than in the definition. And some functions are neither convex nor concave. The reason we care about convexity when we are thinking about optimization is because, remember calculus where you want to optimize a function, you want to say find the minimum of a function, you take the derivative and set it to 0, or you take, and at that point you only know that it's either a minimum or a maximum. To test if it's actually a minimum, you take the second derivative and check if it's positive. What you're actually checking for is the function convex. So if you set the derivative to 0, or in high dimensions, the derivative is represented by this nabla, the gradient of the function is 0, which means the tangent is basically horizontal. If you're imagining the function the way I do. For convex functions, this condition of this gradient being 0 equals global minimum is necessary and sufficient. So if I have a convex function and I want to minimize it, all I need to do is to find a point x where the gradient of that function becomes 0. And then the convexity of that function guarantees that I am sitting on the minimum, the global minimum. All of this directly translates to things that we've seen for functions of one variable. In multi-dimensions, unfortunately we go from numbers to vectors and matrices. But the math and the intuitions remain the same. Questions about convexity? How many people have seen convexity before in some other context? About half the class. So for the rest of you, this may or may not be the most obvious thing in the world, but I find it useful when I'm trying to reason about convexity to think of the one-dimensional case. Very often your intuitions carry over. So if you've never seen this before and you want a one-line summary, convexity is a good property to have when you want to minimize functions, because I can now minimize by just going down the gradient, which means gradient descent works. SVM function, the SVM objective, is a convex function. And the way to prove that is to use some properties of convexity. It's a sum. So let's analyze the two pieces separately. The first term is W transpose W. W transpose W is just like x square or W square. It's W square plus W2 square and so on. So we know that squares are convex functions. So the first term is convex. The second term is basically a max applied to 0, a line. We know that lines are convex and max is convex, and another property of convexity is composing two convex functions gives us a convex function. So max of 0, 1 minus y W transpose x is convex. Yet another property of convex functions is if you have two convex functions, you add them up, you get a convex function. So the first term is convex, the second term is convex, you're adding them up, it's convex. So the SVM objective is convex, which means in order to minimize this objective, all I need to do is to find a W where the gradient is 0. It's an infinite set of, it's an infinite space, a vector space, but we can come up with efficient search function ways to do this optimization. This kind of a optimization problem is called quadratic programming, and when the SVM objective was first written down, a lot of people got so excited. I mean, it's QP, quadratic programming. All I need to do is just give it to a QP solver and life is good. And that was pretty much the state of the art for a while. You just you write down this objective function, give it to a QP solver, and that was the way to train an SVM. Turns out QP solvers for this thing are very slow, and there's no way to scale. And so gradient descent has become one of the more dominant methods. Not exactly gradient descent, but variants of that. We've seen gradient descent before, but before talking about gradient descent and all those such things, questions about this function, its convexity, or generally in convexity.
So there is no analytical solution for it?
There is no analytical solution for this. Yes. You can't take the derivative of this and set it to 0 because, this cannot be solved on paper. Other questions?
How slow is slow?
How slow is slow? It scales with the size of the dimensionality and with the gradient, with the size of the data set. I don't remember the details. It might be linearly in those things, so it's not too good. Or maybe even more than linearly. So the first thing that you should think of when you see convex functions is, as you said, can I solve it analytically? If I want to say, find the minimum of x squared, then I just take the derivative, I get 2x, I set it to 0, and I say that x equals 0 is a solution. That's an analytical solution. I did not have to run a program, I just solved it on paper. In this case, it can't be solved analytically. The next thing that you should think about is, can I use gradient descent or some gradient-based method? So, to remind you, we've seen gradient descent before. Gradient descent is a general strategy for minimizing convex functions. So you have a function j of w, and what you do is you start with some initial guess, w0. The gradient is simply the direction. The gradient is, you take the first derivative, and that's the direction in which this function increases the fastest. Think of it, imagine, climbing into a valley, and you want to get to the bottom. And you are standing at a point, you look around, you find the direction in which this valley is the steepest, is going up the steepest. And then you choose the opposite direction. So you compute the gradient, and you go down. Basically, you take a step in the direction of the negative gradient. And you keep doing this again and again till at some point you just taken too many steps and you want to stop. This is the general intuition behind gradient descent, and you have a question.
When we take our original weight 1 guess and our weight 2 guess, are we going to just increase one element?
The entire vector.
So increase all of them by some amount?
Yes, increase or decrease or whatever, update. Yes. So that gives us the gradient descent algorithm for SVM. So the story is not done, so let's not celebrate yet, but here's an algorithm. You initialize some weight vector, W0, and you take multiple steps. At each step, you compute the gradient of the objective function. I'm calling it j of w, and that's just your SVM objective. You compute the gradient of the objective function. That gives you a direction, and I'm calling it nabla j. At that point, at wt, and you take a step in the opposite direction. So wt plus 1 is wt minus some r, some learning rate, some step size, times the direction of your gradient. This is your general strategy for gradient descent. And we've seen something like this before in the context of least mean squares. So in fact, this slide might even be the same thing with a different objective. Yes?
This may be a after class question, but if we can compute the gradient, why can't we solve this analytically? why can't we, piecewise figure out what the minimum should be?
Try it out.
Okay.
You can't solve it analytically because you'll get an equation that says this value equals 0, and you can't solve that equation easily.
Okay. But that doesn't mean that there isn't a solution.
No, in this case, I think there isn't.
Oh.
I suspect there isn't. I'm fairly certain there isn't. Yes.
How can you differentiate the max?
How can you? Aha! Excellent question. There's a max here, right here. And I've been talking about taking derivatives. Max is a function that looks like this. Your Hinge loss was a function that looked like this. You can take a derivative at any point along here. You can take a derivative anywhere point here. At this point, it's not differentiable. We'll have to make another. There are 2 more tweaks left, and that's the second of those. The first one, though, is something more. Is a computational issue. I care about finding the gradient. It doesn't matter that even if I had a way of computing the gradient of max or some approximation or something like that, I still, every time I have to compute the gradient, I have to sum over the entire thing, because the gradient of the derivative of W transpose W is with respect to the vector. So this is vector calculus. So you have this function, partial derivative of this function with respect to W is simply W. It turns out that's like saying the derivative of x squared with respect to, or actually it's 2W. The derivative of x squared with respect to x is 2x. W transpose W is just like W squared. So that part is easy. And now I have to take the derivative of this entire sum, every element. So in order to compute one gradient estimate, I have to sum over the entire training set. I have to, and we live in the world of somewhat biggish data, not very large, turns out, but it's often computationally inconvenient to take derivatives over the entire training set. And that's going to hurt us. And the answer is the same thing that we saw when we were looking at least mean squares. The answer is a variant of gradient descent called stochastic gradient descent. And this is actually a very cool idea. You have a training set, and I'm going to give a version of this that's tailored to learning and that's tailored to this kind of setting, this kind of an objective, but this is a general strategy. You have a training set, a set consisting of S, I'm calling it S, let's say has M elements, and I can write down the SVM objective as the sum of Hinge loss over all those M training examples plus a regularizer. And I can take a gradient and all that. And that's painful, so what I will do is pick a random example, just any random example, and pretend that one example is the entire training set. That's all we have at that point. And you write down the SVM objective just for that one example. So it is the regularizer plus C times the sum over that one example. So basically there's no sum of the Hinge loss. So you write down this objective here and pretend that your entire training set is summarized in that one example. You take the derivative with respect to that one example, with respect to W at that point, and take a step. And that's one step. And then now again randomly pick another example, pretend that that's your entire training set, take the derivative, take a step. So, and keep iterating. This strategy is called stochastic gradient descent. It's stochastic because you're randomly picking training examples, pretending that it's the entire training set, and taking a gradient step. And you do this many, many times, and you return the final weight vector. This strategy for learning is called stochastic gradient descent, and the reason it works, and actually it works, and not only does it work, it comes with guarantees that this will converge to the bottom of that convex function. The reason it works is because this function is convex. This is a general strategy for optimizing convex functions that look like big sums. And it converges with, there are some caveats, your learning rate, and I'm calling it gamma t, the learning rate has to satisfy certain conditions, and it's very easy to satisfy those conditions. So this is probably, stochastic gradient descent is probably the default learning algorithm. You remember I was telling you about how the recipe for writing learning algorithms is to write down this objective, which is the sum of some regularizer plus some empirical loss, and you reduce it to an optimization problem. This is the most commonly used algorithm for solving that optimization problem, because your objective looks like a sum. The empirical loss is a sum over the training set. And stochastic gradient descent is very often the default algorithm that's used for solving these problems. Here's a pretty picture. This is from Andrew Ng's talk. The one on the picture on this side shows how gradient descent proceeds for some quadratic function. Here, this is basically level curves of that function. Gradient descent is guaranteed to reduce the value of the objective at every step. It just goes down the gradient, and every step will, with some caveats on the learning rate, every step will reduce the objective. Stochastic gradient descent is that somewhat squiggly pink line. At any one step, there's no guarantee that your objective, the total objective will decrease, but in expectation, if you run this enough number of times, you will get to the bottom. So basically think of this is like a drunk walk. So, and it has some fantastic computational properties. So just to put this into some context, what you do is you, again, just like we did for perceptron, the learning proceeds in multiple epochs. At each step, you pick an example and you pretend that this example is your entire training set, compute the objective, compute the gradient of the objective at that current weight vector, and take a step. Question?
In stochastic descent, how do you know that you're at the bottom?
You don't actually. In fact, that's a good question. How long should you continue this optimization? Because there's no, you might have gone down a bit and then you might eventually come back up a bit and such things. You have no way of knowing exactly that you're at the bottom. Very often what you do, there are two strategies. You run it for a fixed number of iterations and you hope life is good, option one. Or option two, you keep track of the objective for some long duration of time, and if the average does not change much. Yes?
Why when you take random example, can't you pick something else?
In practice, you will be picking in some order, but the randomness is what guarantees the convergence. In fact, you have to introduce randomness while picking examples. So now let's come to the second part, the second somewhat uncomfortable problem we had. The first problem we had was gradient descent is too slow because at every step to compute the gradient we are summing. The second question in a minute. Second question was that the Hinge loss is not differentiable. We'll get to that in about 30 seconds.
I was going to ask about gradient descent.
Yes.
Well, stochastic gradient descent actually, and how it compares, because clearly it seems like you're going to be taking more steps to stochastic.
Yes, you'll be taking more steps, but each step does less work.
So,
and what happens actually is that you converge faster because each step does a little bit of work, and the total number of there's actually a formal guarantee. I'll show you. It turns out stochastic gradient descent for SVM, the convergence, you can get to a good enough solution in number of steps that's independent of the training size, and that's really fantastic. And we'll see that in a minute. I mean, maybe in the beginning of the first thing in the next lecture, but we'll see that very quickly. Yes.
So is it possible that we're not going through each training example since we're just picking a random one?
Yes. In fact, that's actually a very astute point. In this setting, it's possible that there are some examples, there's a non-zero probability that there's some example that you never pick, because you're picking examples with replacement and you may never see an example. And to counter that, what you do is you actually do learning in epochs. You have an epoch, within that you first shuffle the training set and iterate over the entire training set. And then shuffle again, iterate over the entire training set. And that guarantees that you see every training example. And that is actually the practical implementation of SGD. So now, in the 3 minutes that are left, probably I'll not be able to get to what's the solution, but I want to point out the problem. All we need to do next is to actually instantiate this algorithm is to compute the derivative. So we want to compute the derivative of this, the stochastic estimate of the objective at some training example, this function here. We can't compute the derivative because the Hinge loss is not differentiable. This thing inside red is not a differentiable function. And the solution there is a new concept. Probably not all of you have seen this before. It's an idea called subgradients. It's a generalization of gradients called subgradients, and I'm going to stop with this detour right after I finish this. It's a generalization of gradients to functions that are not differentiable. And in order to get to this generalization, we have to think about what a gradient is. The gradient is the slope of the tangent. A tangent is a line that lies below the function, or a plane that lies below the function everywhere. A subgradient, or a subtangent actually, is a line that satisfies the same property. It's any line that touches the function at a point and lies below it everywhere else. And the subgradient is the slope of that, the slope of the subtangent. This picture is actually from a slide by Stephen Boyd, he's written the book on optimization, where there's some function here, and this function is differentiable everywhere except at this one point at x2. And there's a formal definition for subgradient. It's basically the subgradient G is G. If there's a formal definition, you can look at it, but the intuition is at point x1 it's differentiable, and this subgradient is really a set of directions, and at points where the function is differentiable, the subgradient is just exactly the same direction as the gradient. It's a set containing one element, namely the gradient itself. At points that are not differentiable, you try to find lines that lie below the line and touch the function at that point. So in this case, at this point x2, there are many such lines. Here this picture just shows two of them, but I can draw more. All of them define the subgradient, or any of them define the slope of any of those lines is the subgradient. So the last thing I want to do, and I'll pick it up here again in the next class again, is to point out that there's a general strategy for calculating the value of the subgradient of max, in particular for max. I want to calculate the gradient for max. What I do is first solve the max. So at a given point, say I have w, y and x, I want to calculate the gradient at w. For that w, first solve the max. So max of these two quantities can either be this or this. So what I do first is, if the max is 0, then this entire thing disappears. So the gradient of j is simply from this part, which is this w. If the max is not 0, then it has to be this line. Then the gradient of the line is the gradient of, it's a differentiable function, I can compute the gradient. And this gives you a strategy for compute, and it turns out now we can actually write down the stochastic subgradient descent algorithm for SVM. I'm a minute over time, so I'm not going to show you the algorithm. I encourage you to try to write it yourself, and we'll see if we agree.